In this section of the video, we're going to talk about subnets and look at all of the potential subnet masks that are available. So previously we've talked about how subnets are just a section of an IP address space for a network. What a subnet mask does is it helps divide an IP address into the portion of the IP address that represents the network and the portion that represents the host. This was in addition to the original IP address scheme called classless interdomain routing, or CIDR for short, which allows us to flexibly allocate subnets. So let's take an IP address. Let's say your wireless router has an IP address of 192.168.0.1, which is actually one of the most common IP addresses, default IP addresses for wireless routers. That's because this is in the one of the private address spaces, which we've talked about. The 192.168 range is private IP address space. And let's say that we're using the 255.255.255.0 subnet mask, which is also one of the most common assigned to wireless routers. So in this case, our subnet mask in binary looks like this. We have 4 octets, 3 of which are all ones. 255 corresponds to all ones in binary. And 0 obviously corresponds to all zeros in binary. So what that means is that in this case, the IP address up here that we have, 192.168.0.1, which we could translate into binary if we want, and we will in later examples. But what that means is that the split between the network portion of the IP address and the host portion of the IP address happens right at the border of the octet. Okay, so right where the dot is at. So that this first half of the IP address, 192.168.0, represents the network portion of the address, and the last octet, the 1 in this case, represents the host portion. So the way that we draw that out in shorthand is we identify the network as the lowest number in that particular IP address range. So the lowest number in that IP address range is 192.168.0.0. So anything that begins with 192.168, that's the lowest range that has this subnet mask where the split is right on the octet with the last octet. This is the network address. Now, we actually don't use the network address in our IP addresses when we assign IP addresses out there. There's actually 2 special IP addresses that we just don't use. The lowest one in any given IP block we don't use. That's the network address. It's used for routing decisions, but it's not used for assigning hosts. And the highest IP address in any given range is defined as the IP broadcast address, which is used for some protocols and some other things. So in this case, we have this last octet to assign hosts. So if we had 8 bits and we could assign 8 bits worth of hosts, that gives us 256 potential numbers that we can use between 0, which is all binary zeros, and between 255, which is all binary ones. All of that section could be assigned to different hosts, except that we have to reserve 2. One for the network, which is the lowest number in a subnet, and one for the broadcast, which is the highest number in a network. And so in this particular example, we can assign hosts between 192.168.0.1 and between 192.168.0.254, which is the highest number that's not broadcast. 192.168.0.255 is the broadcast address for this subnet. Now what if we wanted a different subnet? Could we have a different subnet with the same subnet mask? And the answer is yes. So this particular subnet mask defines subnets that are a maximum of 254 hosts in size that use the last octet. But what if we were to use a different IP address? For example, 192.168.2.1. What if that was our IP address? Well, in that case, with that IP address and with that subnet, the lowest IP address, the network IP address, would be the 192.168.2.0. That's the network address, which we don't assign to any hosts. And the broadcast address becomes 192.168.2. Whatever the highest number is based on this subnet, and that happens to be, in this case, 255. And so the first host is the one that we have right here, 192.168.2.1, and the highest host that we could assign would be 192.168.2.254, or one less than the broadcast address. Now it does get a little bit messier when our subnet masks don't break exactly on the octet, and so we'll do some more complicated examples next. But before we're going to go into more complicated subnet mask calculations, let's look at all of our potential subnet masks. So you'll notice in binary, the largest number subnet mask we could potentially use would be all ones. And so that would be 32 ones, or 4 octets of 255, 255.255.255.255, all ones. But what that means is that all of the IP address is the network portion, and none of the IP address is hosts. So because of that, there's no host portion of that. It's actually completely unusable. So we don't use that subnet mask. The next one down is all ones except for the last value, which is 0. That's the shorthand of 31, because there's 31 ones in the subnet mask, or 255.255.255.254. And the problem here is, well, we don't have room for a broadcast address and a network address and a host, because we only have 1 bit at the end, or 2 potential spots that we can assign. And because of that, we actually can't use this one either for host, because it doesn't have enough spots. So these top 2 are really unusable. But after that, we can use any of these other subnet masks. Each of them gives us a different number of hosts. So for example, this 255.255.255.0 subnet mask that we just used, which has the last octet, or 8 bits, as zeros, its shorthand is the /24 network, because it's 24 ones and 8 zeros. And that gives us a maximum number of 254 hosts, which gives us, 256 potential hosts, 2 to the 8th because of these 8 zeros, but subtract 2 because of the network address, which is the lowest number, and the broadcast address, which is the highest number. This also happened to be the original Class C address space when we were doing classless or classful routing. But what if we want to break it up, a little bit differently than that? What if we need some hosts? What if we need more hosts than 254 in a particular subnet? What if we need 300? Well, we could potentially, provided we have the IP address space to do this, we could use a subnet mask like 255.255.254.0, which gives us a maximum of 210 hosts. So with this subnet mask, with the 255.255.254.0, we have 9 bits that are corresponding to the host portion of our network. This is a /23 network, so 23 bits represent the network portion, and 9 bits represent the host portion. Those 9 bits, 2 to the 9th, gives us 512 potential IP addresses, 2 of which are reserved for us. The network portion, the lowest number, and the broadcast address, the highest number. So we have 210 remaining hosts that are available for us to assign. Now the challenge becomes is this doesn't end exactly on the boundary between octets, which means our math becomes a little more tricky. And so let's now, next we'll move to doing the calculations when things get a little trickier like that.